Hello, welcome to our video solution for problem 5 from the first Superquiz. This is about equivalence relations in this problem. And let's see, we're given a relation on the set of real numbers. The relation is called curly R. And it's defined in the following way. If you have two real numbers, then they're going to be related. That is, the pair x comma y will be in the relation R. If the cosine of those two real numbers is the same. So, of course, we know that the cosine is definitely not an injective function. It has lots and lots of collisions. Right? If we were to draw a graph of the cosine function, say we start up here at 1, right? And we come down and up and down and up, and of course it goes the same in the other direction and so forth. We can see that you can choose a lot of different points which are going to intersect, or that is the outputs will intersect this line that I draw at multiple points, right? In fact, an infinite number. So it's very possible, right, that you could have two different real numbers who have the same cosine. Okay, fine, that's okay. The first problem is to show that this actually does form an equivalence relation. And the short answer to this is it's going to form an equivalence relation because equality forms an equivalence relation. But let's go through the steps. So for part A, of course, we need to check the three different conditions of being an equivalence relation. First, we need reflexivity, and then we'll need symmetry, and then we'll need transitivity. All right. So for reflexivity, that is showing that each element in the real numbers is related to itself. Well, what does that mean? That means that cosine of x would have to equal the cosine of x. Well, of course, that's true. So this implies that x comma x is in R. What about symmetry? All right. Well, for symmetry, we would need to check that if xy is in R, then yx is in R. Well, what does it mean that xy is in R? Well, it means that the cosine of x is equal to the cosine of y. Of course, equality doesn't care what order you write it down in. So the cosine of y is also equal to the cosine of x, and so we conclude that yx is in curly R. And finally, for transitivity, we assume that we have a pair x, y, in R, and, well, let's put another one in here, and another pair y, z in R. So if that's true, then we know that the cosine of x is equal to the cosine of y, because xy is in R, and we know that cosine of y is equal to the cosine of z, because y comma z is in R. But by the transitivity of equality, we know that means that cosine of x equals cosine of z. And so x comma z is an element of R. Okay. If you were writing this up carefully, of course, you'd want to say things at the beginning. For example, let x, y, and z be elements of the set of real numbers. All right. But in any case, we've now shown that this relation is reflexive, symmetric, and transitive, and therefore is an equivalence relation. The next problem, part B, is to show that, or is rather to describe all the elements that are in the same equivalence class as pi over 3. Why pi over 3? Well, why not pi over 3? Right? We can take any real number we like and ask what are the points in the same equivalence class. So it might be helpful to draw a unit circle here. So we draw a nice unit circle. And pi over 3 radians, yeah, same as 60 degrees, that would be right here. And what is the cosine of pi over 3? So the cosine of pi over 3 is the x-coordinate of this point. And so this, right, this distance down here, that is the cosine of pi over 3, where, again, this angle measure should be pi over 3. Cosine of pi over 3 is 1/2, because this coordinate is 1/2 comma 3 over 2. Okay, so we're asking now then for what are all of the real numbers whose cosine is the same as the cosine of pi over 3. So that means we're asking what are all of the real numbers such that when you take their cosine, you get 1/2. All right, let's go back to our unit circle. Well, there's two ways of getting 1/2 on the unit circle as the x coordinate. One is being up here at pi over 3. Of course, you could go around again, right? If you go another 2 pi around or 4 pi around, you'll end up back at this point. So if you take pi over 3 and you add any multiple, say k times it, right? Any multiple of 2 pi, you're going to again get some angle or some real number whose cosine is again 1/2. Okay, but we also could reflect this point down below. We could go this direction, take this angle, and that angle, of course, is just the negative of pi over 3, right? So down here, the coordinate will still be 1/2, although the sign will be different, negative root 3 over 2. But we don't care about the sign. We only care about the cosine. Okay, and again, this angle down here is negative pi over 3. And of course, once again, I could go 2 pi around in any direction. So if I had cosine of negative pi over 3 plus 2k pi, this would also be 1/2. All right, so if we denote the equivalence class of pi over 3 by square brackets around pi over 3, then this would consist of all numbers of the form pi over 3 plus 2k pi, or negative pi over 3 plus 2k pi. So we could write down here, if we wanted it really short, we could do plus or minus pi over 3 plus 2k pi, where, well, what's the condition on this k? It just has to be some integer. Right? If negative, it doesn't matter, it just means you're going backward. Positive, you're going forward. 0, not a problem, you're just at the original point, plus or minus pi over 3. So there we go. So this is the equivalence class of pi over 3. Okay. Hopefully this is helpful to you. Have a wonderful day.